Well, to help us explain what's going on here, we need to look at the nature of water. In particular, we're interested in the nature of ocean water. And we can see, at room temperature, water is very fluid. We can pour it over it. Now, the way it changes state helps us understand the nature of it. You can see, you've seen the steams. So water is actually moving into the gaseous state. And we know that solid water happens at a very low temperature. We remove energy, we remove heat, and something changes it. We add energy, we add heat, and something changes to it. When we pour it out, it is like this. If we magnify down and look at the molecular level, and what we've got are these molecules of water, H2O, two hydrogen and an oxygen bonded together. I mean, there are other things dissolved in it. There's carbon dioxide, there's O2, oxygen. And when it's in the liquid state, they've got plenty of energy and they're moving around like that, and they can take up any shape they go into. When they get a lot of energy and heat, they come out of that liquid state and into the gaseous state. Yeah? And then when we remove the energy out of it and lower the heat, then we find that it forms a lattice because these molecules have a charge, an electrical charge by the nature of the way they are, and they attract positive to negative so that they form a lattice work that in the solid form where they just haven't got so much energy, they're not moving so much, that gives them this ice formation. Not only that, but in the liquid form, the hydrogen and hydroxide separate out, so you get an OH negative ion and a H plus ion. So they're always H plus ions, hydrogen ions, and that's something we'll come to later on when we look at pH. That's important. The carbon dioxide, the oxygen. Now, when we added our salt to this, we added sodium chloride. Here's our sodium, our metal, and our chloride ion. These are connected together. Once they're in that liquid, once we've dissolved them into our water, they separate out, and the positive sodium ion and the negative chloride ion are mixed in there as an ionic solution. Because water has that charged molecule nature and pulls those apart and attracts the positive to one end and the negative to the other end, we find it's an incredible solvent. Lots of things dissolve in it in this way and become ionic solutions. So our ocean water, as a solution with some very special properties. It's a very good solvent. It's got a rich complex of ions that have dissolved into that water solution. It's got hydrogen ions moving in and out of solution. It's able to dissolve gases like carbon dioxide and oxygen and other gases. And it's fluid over a very wide range, over the range of temperatures that we commonly find across the planet. Only at extreme cold temperatures does it become solidified. And then, interestingly enough, it expands. If we were to put that ice in this water, for example, we would find that the ice floats. It has less density, less dense than the liquid water, which is very unusual. So these properties relate to this, where we have expansion. As we've put more heat into it, there's more energy. More energy means that molecules are taking up more space, and we see this expansion of a liquid. Now, if we can capture that expansion into a long, thin tube, so we can magnify it up, we have some way of maybe calibrating that and measuring it. At the moment, what we've made here is a thermoscope. It lets us see the effective temperature. What we want to do is turn this thermoscope into a thermometer, which will allow us to measure the temperature.